Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I am super happy to have Wes Fraser with us today. Hello, Wes.
Hey.
Hey, well, thank you for agreeing to talk about your very lovely article.
Oh, my pleasure.
And it is lovely.
Maybe a bit long.
It's packed. Let's put it that way. We will get to it soon. And Wes, where are you located at?
Victoria, BC, Canada. So west
Okay.
coast of the country, right on Vancouver Island, South
Very
Point.
nice. Very nice. Do you have a boat?
I have a kayak, or at least I
Kayak.
use a kayak. I don't sail.
Very cool. Very cool. Very nice. Let's see. It is May 26th, 2023 as we record this. And so is summer starting to peak out a little bit in Victoria?
Yeah, I was just saying to my partner this morning, today is the first day of summer that I've been able to experience here, proper short weather in t-shirts. Yeah.
So I'm quite the opposite here a little bit. So I'm in Phoenix, Arizona, and we haven't quite hit the power switch yet. We are warm, but we haven't banged yet. So it's coming. That'll be cool. Very nice. And Wes, what is your position there in Victoria?
I am a research officer at the Herzberg Astronomy and Astrophysics Research Center. A bit of a mouthful. That is one of 20 or so facilities that are run by Canada's National Research Council.
Yeah, right. Mm-hmm.
I'm also an adjunct professor at the University of Victoria, and then also one at Asia in Taipei. Oddly enough,
I don't want to know where your wave function is collapsing. Wild. And Wes, what do you like to do for research?
I like to study the Kuiper belts. The sort of the one sentence summary I like to give people at, when I'm getting my haircut or drinking a beer at the bar or whatever, is I like to understand why, or I like to try to understand why Pluto didn't grow up. I think that betrays my real interest.
I have never heard that. That's pretty.
Oh, it's good. I don't think I coined that, but it's certainly usul.
It's very useful. It gets it across in a nutshell.
Yeah,
it's very beautiful.
20 years of trying to answer that question, eventually get it right. I'm less interested in the Kuiper Belt per se, and more interested in knowing what the Kuiper Belt tells us about how the solar system formed and how planets grew and that sort of thing. Yep. That's where my real interests are, is understanding planet formation.
Awesome. And this is going to bring us to a very awesome planetary science journal. But before we do that, we're going to get a little orienteering. And so, Wes, why don't you orientate us a little bit here?
On
the figure, if you want to put the figure up.
Oh yeah, sure. Well, let's share this here.
That's what I meant by orienteering.
Yeah.
Where are we looking here?
So the AAS, or Outer Solar System Origin Survey. I'll scroll up to the top here. This is a paper written by one of my excellent colleagues, Michelle Bannister, who has moved back to New Zealand and taken a professorship there. She helped run the Outer Solar System Origins Survey, or AAS, and this was a survey done on the CFHT, who observed. This is a top-down view of the solar system. All of those blue dots that you see there are real Kuiper Belt objects that they discovered in this survey, and it's run on the Canada, France, Hawaii telescope.
800 of them.
Sorry, go ahead.
800 plus.
Yeah, exactly. I think the final count was closer to 900, with 830 something like that characterized. And this is actually that's a really important word here. What they did was observe in these 8 what we call blocks or wedges, and each block or wedge was of course observed at a different time of the year and different weather conditions and so on. And so each one received a characterization that describes how sensitive the survey was to a given rate of motion and a given depth and in a given location. And so this is actually very, very useful from my perspective, because it allowed me to then go off and observe these objects for different purposes, but knowing their discovery circumstances. And so this was the real power of AAS.
Yeah, nice.
Something that I've been interested in trying to understand for a long time now, back since 2009 is when I started doing this, is to understand the surface compositions of Kuiper Belt objects.
Ooh, yes.
Yeah, and so this is a bit of a switch from this sort of discovery survey that Michelle ran. What I'm interested in knowing is what the bulk compositions of the Kuiper Belt are, because you can imagine exactly what the material makeup that you typically find in the outer solar system is an important factor in understanding how objects grow, right? So if you're icier versus rockier, you're stickier versus less sticky. It tells you a lot about the thermal history of these objects and how hard the collisions were that grew bodies from dust upwards, that sort of thing. You can also use the compositional distribution of the Kuiper Belt as a means of informing us about the compositional distribution of the protoplanetesimal disk. And that's actually where Col-OSSOS came in. And the idea for Col-OSSOS, or Colors of the Outer Solar System Origins Survey, bit of a mouthful. We were using optical and near-infrared colors of objects discovered in OSSOS to try and provide a map of the compositional and dynamical outer solar system that we currently see, so that we can then sort of map that back to the early solar system before the gas giant planets moved around and that sort of thing.
Right.
So that brings us to that my paper.
Okay. And we will bring up this very lovely PSJ article.
Thanks.
So number one, it is open access, people. You can go get a copy for free. We are in the open access era. Go grab one.
That's the only way to be. We should have been there a long, long time.
Oh, that's a whole nother video.
No kidding.
And we have Col-OSSOS.
Yeah, so two types of Kuiper Belt surface. So I'll get there in a second. I want to shout out to all of my co-authors here. This isn't all of the people that were involved in Col-OSSOS. There are a few more for our early papers that didn't get themselves involved in these ones. But you can see in the top right there's Michelle again. She was a very big player. Michelle, Rosemary, Meg, Mikhail, and JJ were the ones that helped me write the proposal way back in the day. And this was so the Gemini telescope, which sits basically directly next door to CFHT, is where we ran this survey. And at the time that I was a Plaskett Fellow here in Victoria, they had a call for large programs. And so it was like, well, okay, time to shoot for the moon, so to speak. So we applied, and what we originally asked for was a 4-year program. And it was a successful application insofar that we were the #1 ranked program on Gemini, which was great. Gemini North, I should say. But they cut us down to 3 years because they decided that a 4-year LP to start was too long. And so we only got 3 years. And so instead of being able to do all 8 of the blocks of OSSOS, we only ended up being able to fit in 5. Exactly. And so, I mean, we still, instead of it being about 130 or 140 objects in Col-OSSOS, we got a bit more than 100, which is still a pretty good number. And the idea was to gather optical and near infrared colors of these objects, and we chose these bands because we realized that they were the ones that were sort of the most informative about, so G, R, and J. G and R, it's like sort of green and red in the optical, and then J band is one of the first near infrared bands that we can get from the Earth. And these were chosen because they seem to be the most compositionally informative for what we knew about Kuiper Belt objects leading into this work. Right. And so the Kuiper Belt objects, their spectra, which is, basically the colors of light reflected off of their surfaces back to the Earth. You can see in the optical, they're very red, much actually the same way as skin or bitumen that comes out of the Earth. It's actually the same sort of process that colors that. Cool. It's just, we speculated that it was organics, but it doesn't really matter what exactly it was. It was trying to measure the color in the optical, because that is informative about things like irradiation processes and how much organic there actually is, that sort of thing. And then J band was in the near infrared because they don't go red for forever. Eventually, the spectra turn over to become much more neutral, and that is informative of other things like how much carbon might be on the surface or how much water ice, and these sorts of things. And so G, R, and J were sort of the minimum filters necessary to give us a handle on the type of object. We don't get specific compositional information from this, but it allows us to build up a taxonomy.
Good.
That makes sense? Yeah, okay.
Yeah, I'm with you. Right. I'm with you.
Yeah. And so then I think the reason why we got this time is because this is the first ever, this maybe still is the first ever colors survey that has all of the features of a survey that astronomers really like brightness complete. Up until this point, all color surveys done, including my own, to be fair, were not brightness complete. They were sampled off of what was known in the Minor Planet Center, and objects that had good orbits, so were targetable by, say, Hubble Space Telescope or something like this. But the sample selection that went into it was always a bit of a mess.
Yeah.
So trying to do statistics on a sample like that was actually very, very difficult. Yeah, exactly, indeed. We also went choosing filters that were sort of applicable to past surveys, so that when we knew what we were doing with this one, we could then take that information we've learned and apply it back to those other past surveys. That sort of thing. And so off we went chasing.
Happy hunting.
Yeah, happy hunting indeed. Yeah. So then a little bit just before we got going, AAS had a meeting in I think it was Marseille. I think it was Marseille. It doesn't really matter. A meeting where because of some fortuitous circumstances and good weather, AAS had about 10 hours spare to do something, and they brought up to the whole team, hey, what do you want to do with this extra 10 hours? Do you want to go get more orbits or what? And I waved the flag. I would actually like to see some U-band. So this is basically the shortest band that an image would be taken in from the ground before the UV cutoff in the atmosphere. Exactly. So we get this U minus G color from this. And I said, hey, it would be really neat to get U on some Col-OSSOS targets, because only one other paper in existence has ever tried U, and they had a small sample, and I saw some interesting things, but there wasn't really much conclusion that could be made. And everyone liked this idea, which was awesome. And so we went with the plan, and it turned out that CFHT then made us the offer to try and observe at exactly the same time, the same targets as we were observing with Gemini.
Oh, very nice.
Which was stunning.
Yeah.
And then finally, just to really rub it all in, JJ, one of my co-authors there, he was at Subaru with a few spare hours on the first few nights of our Col-OSSOS run. And so we had CFHT, Gemini, and Subaru all observing the same targets at the same time.
Very cool.
That ended up leading towards CFHT saying, this is really neat, we'd like to participate for the entire survey. And so we did have to apply for this time, but they became an integral part of the program. So really, Col-OSSOS was a dual telescope program, which was stunning. I've never had that luck before.
I've not heard that too often.
Yeah, exactly. Let's take a look at figure 1. Let's actually see what we did here.
Thank you for that. Lovely. And there's some really awesome tables in here in this article.
Yeah, table 1 was just like this is just a summary of that figure that I showed you from Michelle's paper.
Right, and so these are 6 of them.
Yeah, exactly. There were ST is sort of one block. It's the same wedge that was broken up into 2 for practical reasons.
Okay.
And the E, O, H, and L were the others that we were able to fit in. And so we skipped a few of the high inclination blocks because there were fewer targets. But anyway, yeah.
Good. And
if you really want the data, all of our filter measurements, every single image we ever took, which is thousands of them, is available in this table 2.
Very good.
The beast, but it's hopefully parsable.
It's machine readable, so you can get the full table in plain old ASCII format. So go grab it, folks. And we got the reductions. We have this monster color table.
Yeah, these are the colors and uncertainties. We produced colors in a couple different filter systems so that people can choose whichever sort of religious preferences they want and go from there. So there's pan stars and SDSS colors.
Nice.
See that a number don't have R minus Z or U minus G. That's because, so for U minus G, we didn't get detections on everything because U they're very, very faint. And Z band was, we fit that in where we could, where weather was good, but weather wasn't always good. And it wasn't originally part of the program. So that was just sort of luck.
A little bonus there, a little bonus.
Exactly.
And Subaru colors. There we
so
go.
These are the few nights that JJ was at the Subaru telescope, gathering whatever filters he deemed to. And so again, it was sort of a random sampling there, which is not that brightness complete thing that I was talking about. We're actually only brightness complete in GRJ, but Z, I, and U have all been very informative as well.
Indeed. Very cool. And we will get to figure 1. Let's see what we found.
Yeah.
And we'll go global first and zoom in.
Yeah, zoom in on the left. That's a good place to
zoom in on the left. We will start on the left. All right, here we
What
go.
we're showing here is G minus R and R minus J. So these are the main colors that we asked for when we first proposed for the LP. And every single target in Col-OSSOS has these values. The idea was we were going to we did for a while actually tune the durations of the integrations according to the discovery brightness as seen by OSSOS. And the idea was to try and give a homogeneous measurement quality in both bands, or all three bands, excuse me, for all targets. Makes statistics a little easier. Unfortunately, due to really, really bad weather in 2015, we ended up having to bleed into normal Q well past the end of the LP to try and get to finish off the program. And it became very difficult for Q observing to finish these observations because Gemini is risk averse, understandably, and so these long sequences that we demanded of them were never getting observed. So you can see, for instance, in the bottom right there, there's a couple red and yellow points that are much bigger error bar. Those are late time targets, where the smaller ones are all the ones we did 2014, 15, and 16. Oh well. Anyway, what we're looking at here, black points are well, maybe start with the red and the yellow. The red and yellow are what we call cold classical Kuiper Belt objects. Cold because they're on low inclinations. They're all found near the ecliptic. Classical because if you went back and asked Edgeworth and Kuiper what they would expect to see in the outer solar system when they predicted the existence of the now Edgeworth Kuiper Belt, they expected to see a band or an annulus of low inclination objects. They're classical objects. All the black ones are dynamically excited things. So these are found well off of the ecliptic with much larger inclinations. They also have larger eccentricities, so their orbits are oval. Some of them are in mean motion resonances. So these are basically objects whose orbits are governed by the presence of Neptune. Pluto is one of those, actually. Exactly. And so yellow and red are cold classical. The red ones are cold classical based on what we call free inclination. And so it turns out that the inclinations objects have near Neptune have a bit of their inclination forced by the dynamics of Neptune itself. And so you can remove that component and look at just the component of inclination that they naturally have. And so depending on who you are, if you're a dynamicist or an observer or some mix of them, you might actually want to know how they're classed in different ways. And so we showed both of these here. The dotted lines you see, the straight lines that connect a bunch of these points together, these are repeat measurements of the same object. So the straight lines there, the black ones that is. And so you can see in some cases there are objects that have, between visits, inconsistent colors, which is an exciting thing because it tells you that they have some variations in composition on their surfaces. And then those two lines that you were drawing out there, those are really the meat of the paper. So the black line is what we call the reddening curve. And I don't like this term very much because it doesn't really contain much about what it actually is. So imagine you have a reflectance spectrum, and imagine you are on that reflectance spectrum as a straight line. So whether it's neutral or blue or red, my is a straight line. And now you observe at filters 1, 2, and 3, R, G, R, J, different wavelengths. If you're on a straight line, it means that the spectral slope or color between pairs of bands are also the same. And that means you are on the reddening curve. Okay. So the further you go along the reddening curve to the right, the redder the object is, but the spectrum is still linear. If you go to the right and below the reddening curve, it means that in G minus R, you are redder than in R minus J, and so you have a concave spectrum. If you are above that curve, you have a convex spectrum. And so that's the utility of the reddening line, is it allows a visual sort of representation of what you might expect the object's spectrum to look like. And you can see for yourself that most of the objects in our sample, and it's true in general, most Kuiper Belt objects fall on or below the red curve. right?
Yes.
And you can actually kind of see the curvature of that curve in this figure here, right? There's a nonlinear structure that these objects have.
Right.
If you wouldn't mind zipping to figure 2.
Yeah, one question before we
Oh,
start.
sure.
Got 3 objects with blue
Oh,
halos around them. They look
yeah,
special.
sorry.
They look special.
Sorry, they are special. Yes, I should have mentioned this. It's one of my favorite discoveries, actually. These are what we call the blue binaries.
Blue binaries.
Yeah, so back in
Okay.
2015, on one of the few good nights that we actually had, Michelle and I were observing at Gemini, and we were looking at one of our objects we zipped to, and you can immediately see that it was a binary Kuiper Belt object in the sense that it's not just one object, but sitting on top of each other in the image. And
oh yeah, sure. Okay.
those are fun, right? The KBOs, we know that there are a bunch that are binary. Most of them are cold classicals.
Yeah.
And we, work of many people before us demonstrated that there's a large number of these, maybe 30–40% of the observable sample is binary, which is surprisingly high. And so it was unsurprising to start seeing these in Colossus, and we have a few. What was very surprising to see is a number of these binaries showing up with blue or nearly neutral color surfaces.
Yeah.
What we know about cold classicals, they aren't just binary. They don't just have a large fraction of binaries. They're also mainly red, right? You can see most of the red points are on the right half.
Yeah.
But the red is to the right and up. And so cold classicals are very, very red reflectors. They have high albedos, they've got very red surfaces, and they have a high binary fraction. But lo and behold, we could immediately see this one binary that we discovered that night wasn't red at all. It actually had a nearly blue surface.
Yeah. Very
that
cool.
was that one you can see at a G minus R of nearly 0.6 and a R minus J of 1.2, that low one. Yeah, exactly. That was the first one we discovered.
Okay.
And so that was really surprising to us. And it was actually a rough discovery to make because it prevented me from getting any sleep the next day for observing the next night. But anyway.
Did you get to name it? Did you get to name it?
We don't get these things aren't named yet. I might be once they are. How does it work? I think they are.
You gotta go IAU.
The orbits are tracked long enough to be designated as numbered, then you can propose to the IAU, and they will accept or deny, right?
Yeah.
Anyway, we haven't done that yet.
Very cool.
But we realized there was a number of these blue binaries, not just in Colossus, but everywhere. And it's odd because they're all blue and they're all binary.
Yeah.
No, the prediction we made in my 2017 paper was that if you found a blue colored cold classical, it would definitely be binary. Or the other way around, if a large number of the binaries could be blue, but the blue forward was always the interesting one. And we realized what that was telling us is that at least for some large fraction of the Kuiper Belt, they were only forming in binary pairs in the early solar system. You don't find singlets that come out the other end of whatever process occurs. It's only binary. And oddly, the compositions are tied to that. And so what we think is there was a region of the disk formed in that gives us the blue color because the location of the disk, or sort of the distance from the sun, determines how hot the material is and therefore what composition
chemistry will happen, right?
And then the conditions were such that when objects were, collapsed, or when dust was collapsing to form objects, it broke up into binary pairs that remain in orbit. They have the same compositions like we see, and they're all in binary pairs. And so this is an interesting thing, because if we can figure out where in the solar system they came from, then these blue binaries actually provide a very, very strong constraint on the conditions during formation. And it's exactly what Colossus was trying to do, to find a signal like this. So that was a very, very neat discovery. Sorry, rant on a completely
No. Discoveries are cool. I learned something new. Blue binaries. That's awesome.
That was a wild one. So we published that in Nature Astronomy a few years back and have been testing it ever since. So
very cool. Well, congratulations on those discoveries.
Thank you.
And we will take a step back. We were talking about these reddening curves, so we're going to
let's zip to figure 2 for a sec. Yeah.
Oh, you want to go down to the
just number 2.
Curve? Number 2. Okay, sorry about that.
No, that's okay.
Let's go to number 2. Figure 2.
Next one down.
There we go.
So here's an aside. These are the G minus R and R minus I. So I is a shorter wavelength than J. It's still in the optical band, but it's still somewhat infrared. That's where that I comes from. These are the optical colors of Trojans. So these are asteroids in the Trojan resonances with Jupiter. And they're somewhere between rocky and icy. Fine. And that black line there is the reddening curve. And you can see for yourself that Trojans basically fall on the reddening curve as well. The contours behind there you see a lot of points. Each one of those black points is actually like 6 or 7 objects together. So the contours are trying to show you where the objects fall. And so it dawned on me one day that actually, no, most of the outer solar system's objects fall on the reddening curve. So let's just get rid of it. I'd like to get rid of it because it might reveal some dynamic or some compositional structure.
Yeah.
Right. And so let's go back to figure 1.
Okay, I'm with you. Figure 1.
And on the right is the reddening color removed.
Yep.
The reddening curve removed, excuse me. And so the idea is for each object in the G minus R minus J space that we measure, you start from the solar color, which is in the bottom left of the left panel there, and you move along the reddening curve to find the spot, the point on that curve that is the closest perpendicular distance to the object.
Okay.
The length along that curve is then what we call PC1 in the x-axis of this plot, and the distance from the curve to the object is what we call PC2.
I'm with you.
If that's confusing, Appendix C1 shows the diagram. You can go take a look at it yourself sometime. But anyway, the idea is we remove this non-linear curve from the structure, and we end up with something that's a lot more rectilinear, as it turns out.
Yes.
And so you can see now the histograms in PC1, it's just sort of a blob, right? There's not a lot going on there. There's some sample cuts and things, but generally speaking, there's not a lot of structure in PC1. That's really what you see. PC2, you actually see 2 sort of mountain peaks with a dip in the middle.
Yep.
And that was actually kind of when we saw that. The nice thing about this PC curve is we can apply some very simple statistics to ask the question, is this real or not? And from the Col-OSSOS sample, there was about a 1% chance of it being artificial or random chance. And so that was a very informative thing. It also, you can see for yourself that so we draw this dashed dotted blue line here. That's where we think we can divide between 2 different surface types of Kuiper Belt object. You'll see that most, exactly. It's a bit rough. We don't actually have an exact handle on this.
But good.
One of my colleagues, Michael Marseille, who's 2nd or 3rd author on this paper, he's got a paper in review with PSJ right now, talking about exactly where that line really should be. So that should be interesting. Let's see what comes out. You can see for yourself that below the line, there's a lot of red and a lot of yellow. And above the line, a lot of black.
Yes.
So what we think we're seeing here is 2 types of object, 2 types of surface. The objects below the curve, we call them faint IR, and that's because they're below this curve because it means for a given optical color, they're fainter in the near infrared than the object above the curve. And so the ones above are called bright IR.
Okay.
And
IR and FIR.
Because the bright IR ones are mostly dynamically excited objects, the black color.
Yes.
And the faint IR ones are mostly called classicals, which are dynamically quiescent, the red color. And what we know is that the black objects had to have formed closer to the sun, because the process by which you get dynamical excitation pushed these objects from where they formed in the protoplanetesimal disk outwards into the Kuiper Belt. Black objects formed at something like 20, 25, maybe 30 AU, and the red objects formed at 40, 45, and 50, that sort of thing.
Very nice. Very nice.
Yeah. And so this is the other sort of signal that we're trying to look for, is because we can now map the dynamics and the colors together to locations in the protoplanetesimal disk, and then take simulations by the likes of someone like David Nizvorny and get details as to where the dividing distance was between the bright IR and the faint IR objects. And so that's actually work being done by one of our other colleagues, Laura Buchanan. She's got one paper out already and is working on another. And Rosemary Pike is working on the resonance structures of these. It's all pretty neat. Now that we have revealed these two populations.
Now you can go to town on it.
Yeah, exactly.
Very
And
cool.
just to sort of convince people that this was real, if you go down to, it might be figure 5 is my guess.
Okay, figure 5. Let's slide on down. Figure
That one further down. Sorry, figure 6.
6. All good.
Yeah. All right. So this is the same thing, but from hot sauce.
Say that again.
Hot sauce. From hot sauce.
I'm going to say
hot sauce, Hubble Wide Field 3 test of surfaces in the outer solar system. Very acronym. So this was a survey I ran with Mike Brown back in 2011, 2012 with the Hubble Space Telescope, doing basically exactly the same thing we did with Col-OSSOS, only on a different sample, gathering optical and near-infrared colors. Instead of G and R, we have the Hubble's filters. So 606 is approximately R, and 814 is approximately I.
Yeah.
And 139 is just a little bit a wavelength of just a little bit longer than the J band, which is 1.2. This is 1.39. And again, color schemes are the same. When we plotted this up, because of the way the survey was designed, which in hindsight was a bit poor, we didn't see a lot of the structure that we saw in Col-OSSOS. But if you go to the right plot and apply that reddening deprojection that I talked about, you can see in PC2 the same sort of valley in the histogram on the left there as you do from Col-OSSOS. And it's at the same value of PC2. That blue line is the same in both curves.
Very good. Okay, excellent.
So then you ask the question, is this probabilistically real? And it's a low chance of being random. And you say, okay, we kind of have confirmation that this is real, and it's from different independent surveys. Yes, they were both done by me, but they're different telescopes, different times of my life.
Different collaborators, yes.
Exactly. So we're convinced that this is quite a real thing. It's there, and in fact, one of the beautiful things that I had while we were writing up the response to referees on this paper is I got an email from one of my colleagues in the DES survey, and they've exactly the same thing. So there's 3 different surveys all pointing to the same thing, that there's these 2 classes of Kuiper Belt objects.
Verification is a good thing.
Verification is the most missed aspect of science.
That's very important. So was this blue binary, was that discovered in 2012, or was this a post realization it was a blue binary?
You asked that. So this was actually observed by Hubble, and it is a blue binary, in fact, as you correctly surmised. And at the time, we had one. So what we did with Hubble is we'd take 2 images in each band, and then we would use the pairs, the quality of the pair, like how similar the pair was, to ask, is this a good measurement, or was this influenced by cosmic rays? Because when you're floating around in space, those cosmic rays show up everywhere in your images. Indeed. And so we saw that one of the images was influenced by cosmic ray, and by the rules of the survey, we just said, okay, forget about it. This object goes in the bin, unfortunately, because it's not part of the high quality sample. And so I completely and totally missed that there was a blue colored cold classical binary in HOTSUS. Had I seen that back in 2012, we probably would have made the same discovery then that we did with Col-OSSOS 5 or 6 years later.
Gotcha.
So maybe a bit of shame to admit that, but there we are. And so when we went back and what I'm showing here, to avoid that same issue that I caused, I actually am showing all of the measurements from HOTSUS, not just the true high quality sample. That's one of the reasons why the error bars on that one are a bit larger, but it's unquestionably a blue color. And so we have 7 or 8 blue binaries known now, and we still don't understand where they come from.
Cool.
It's fun.
Very cool.
Yeah. I suspect the other thing we want to look at is the distribution of surfaces. So if you scroll down, I think it's figure 7.
Yeah, because that was kind of where we were aiming at on this.
Yeah, exactly. It's all fine and dandy that we've been able to find 2 classes. We'd really like to understand what they tell us. And so the focus of my paper was to understand surface compositions. And so what I'm showing here is G minus R, and then versus R minus J, R minus Z, and U minus G. So remember, R minus J is the main Col-OSSOS
Yes.
red color, and then R minus Z and U minus G come from when we can get them.
Bonuses.
Yeah, exactly. And there, that on the top panel, the dotted blue again is the separation between the bright IR and faint IR.
Yes.
The two red dashed curves
Yeah.
are what I call compositional mixing models. And so this was something that Mike helped me come back in 2012 for AAS. Walk with me on this one. Imagine you have snow that freshly falls on a highway. And this is a very Canadian example.
Okay, definitely not Phoenix, but okay.
Exactly. It's white and it's clear. Okay. Now imagine a bunch of cars ripping through and all the dirt on the cars falling off into the snow. That's black and it's dirty. And then a snowplow goes by and mixes all of that stuff together on the side of the highway.
Okay.
Right. So we have one end member, which is snow, and it's white and it's clear and it's very, very obviously snow. We have another end member, which is gravel. It's black, it's dirty, it's very clearly gravel. And then in the middle, we have a mix of the two.
Right.
So now that's what these mixing curves show.
Gotcha.
We have on one side a material, so on the bottom left there, this material would be considered a silicate. So a rock, basically, because we know that there has to be some rocky component inside these objects. Okay. And then on the top right would be an organic. So we know that we speculated that for years and years, people have speculated that Kuiper Belt objects were red because they're coated in organic. And you can go into the lab and mix nitrogen, carbon, and hydrogen together, irradiate it with the sun for equivalently 4 billion years, and you get red gunk at the other end.
Yes.
And so one of these curves at the top right there, you pick an organic component, and then along the curve is just how much of the two do you mix together. So on the left is more silicate, then as you go further right, you get more and more organic. And what you do is you end up producing a range of colors for one class. Sure. Where the class itself is made up of two common components, but the class itself can also have a range of colors because they can have a range of mixtures.
Yes.
Right. And so we know that there are, we see from the Col-OSSOS and HOTSOS observations that there's actually only mainly two classes of Kuiper Belt. So the question was, can I make two mixing curves that can account for the majority of observations we see?
There you
and
go.
The answer was mostly yes. Obviously, there's a few points here, like the bottom right and the top left there.
Yeah.
That those objects don't fall anywhere near these two red lines.
Right.
But about 80% of the sample is actually consistent with these two curves, believe it or not. And so that was neat. That's one pair of bands, just R minus J and G minus R. But I really wanted to know if that was real or not, right? It would have to be consistent with all of our other measurements to be real or not.
Right.
And so what I did was to say, I'll draw a fake Kuiper Belt surface off of one of these red lines. So, pick either the top or the bottom, and then pick a random color and draw that color off. From that, I have a model spectrum because that's where these curves come from. And then I can resample off of that spectrum into the different bands that Col-OSSOS sees. And so R minus Z down there. And by nature of just the colors that you see when you sample off of the top line and the bottom line for faint IR, which is blue and orange respectively, this is the distribution of R minus Z you get. And you can see for yourself that even though we're sampling off of R minus J, we're actually reproducing the majority of R minus Z as we go. Yeah. And this is true of BVRI when you're looking at other surveys. This is also true of so the old filters, blue, violet, red, and indigo BVRI.
Yeah.
And so you can reproduce BVRI colors of Kuiper Belt objects in exactly the same way with just these two curves. Cool. And you also fully reproduce the HOTSOS colors as well, which I don't show here, but it's true. And so generally speaking, with just two mixing model classes, you basically fully account for the observed optical near-infrared color distribution of the Kuiper Belt. Cool. And so that was where once that came up, it was like, okay, we got this. This is very cool. This is what's happening. It falls down in the U band, which is interesting. You can see right in the U, you just get these two little fingers, and that's because we assume linear spectra all the way through the optical range.
Okay.
And so that's where you get these two tight little bands that fall on top of each other. Yeah. But what the U band is clearly telling us is that they're nonlinear in the U band. And that that's actually consistent with
makes sense.
expectations from organics and silicates mixed together. You would expect things to flat out. And so Nicole Tan, one of my colleagues on this paper, she's actually working on her PhD thesis with Michelle, doing a better job of the U-band analysis than I ever did. A much more thorough sample, a much better analysis, and trying to interpret all of this. So where we did not get it right, I expect she will. I'm very excited to see that coming, actually.
That will be fun to see. Very good. Exactly. Very good. I'm waiting.
And then finally, the last thing probably worth mentioning, figure 8, I believe it is.
Okay.
Figure 9. Sorry, we'll skip this one. That's a bit in the weeds.
So let's go figure 9.
Yeah, so what we're showing here on the bottom is semi-major axis. Sorry, let me back up a sec. These are parameters of orbits of Col-OSSOS and Hot-OSSOS targets. Okay. And so your orbit looks like an ellipse. How elliptical you are is the eccentricity. Yep. How, if the plane of the solar system is my shoulders, how inclined you are, that's the inclination. Yes. And then the semi-major axis is the average distance from the sun. So the bigger that number, the further out you are, basically. And so you can actually see in the top right of this plot, the red points there. Those are they're all faint IR objects, but the majority of them sit in that tight little band around 45 with low inclinations. Those are the cult classicals that we've been talking about all along.
Yes.
The black points in this case are the bright IR objects, and you can see they go up to much higher inclinations and much higher eccentricities. We wanted to ask the question, how different were the orbital distributions of these two samples? And you can just see from this plot, they're really quite different.
Very different.
And so the reason why this is important is because the structure that we see here is tells us about the dynamics that got them there, specifically Neptune's migration. Because the bright IR objects formed closer to the sun. When Neptune migrated outwards like a big bully or a snowplow, they saw much more excited interactions with Neptune and got to higher inclinations and eccentricities. So a paper that's forthcoming right now by Mikhail and actually Rosemary and Mikhail's papers together are studying the detailed version of what I just mentioned here. Okay. We basically wanted to point out that our expectations for if bright IR formed closer to the sun, they must be found at higher inclinations and eccentricities is actually in fact true.
That's a prediction. Nice.
Yeah, exactly. A prediction. Always good.
Predictions that come true are good.
Yeah, well, we'll see.
We'll come back to that. I will come back to that in a minute.
Sure.
Okay.
And so I think that's the majority of the meat of this paper.
Okay. Very cool. Very cool. So there's lots of machine readable tables here. There's some very lovely appendices. If people want to check them out, it's fantastic. And Wes, I want to thank you so much for walking us through this very awesome article on Col-OSSOS. Thank you.
A lot of fun.
And you hinted at it a couple of times there. So let me just push on it a little bit on where do you think we go with this over the next couple of years? Are you going to be putting in another major proposal to do Col-OSSOS 2? And is there additional, you mentioned some of the additional theoretical work, the additional observational work. And so just in general, where do you think we go with this topic over the next couple of years?
There's a lot happening right now. So just
that sounds like a good idea.
There is a lot happening right now related to this work. We have a lot of lab stuff happening right now, trying to understand sort of solar system analogs and what they might be made of and how they get to this red state that we're seeing.
Laboratory.
I have the New Horizons mission to thank for that, I think. There was a bunch of lab work that's been done, but it kind of slowed down for a while. But then when we flew by Pluto and flew by Arrokoth, suddenly we had a lot of new information, and that reinvigorated a lot of the lab work that we're seeing. And so Dale Cruikshank and Roosh and so on, so all the big names in that field, they're producing stuff right now, and it's still pretty early days because it takes a while. But I think we're actually going to get some very useful laboratory analogs that we didn't have before that can compare to measurements like what I make or what they made with the New Horizons flybys to tell us a lot more about specific compositional information.
Cool.
We also have Noemi Pinilla Alonso and John Stansbury to thank for a JWST program that is just about finished up. This was the first, it was a large program accepted on cycle 1. She won, I lost, so good for Noemi. And the idea is they were using the near-infrared cameras on JWST to get spectra of, I think I ended up getting about 60 or so Kuiper Belt objects, which is a
very nice.
Yeah, really cool stuff.
Yeah.
I've seen a lot of these spectra. In fact, Mike Brown and I have a paper in with PSJ right now under review, talking about some of these spectra. And I know Noemi and co have a bunch of papers into, I'm guessing, Nature regarding all of this stuff. And there's a lot of discoveries being made. So one of the ones that's clearly stood out for me, because it hits close to home, is that I said for a long time, astronomers have speculated that Kuiper Belt objects are coded in organics. We have had no clear demonstration that that's actually the case. It's only been a theory until JWST. There is very, very clearly in a large number of these spectra, one of the CH vibrational bands showing an absorption feature in those spectra. And it's exactly where it's supposed to be. Kind of behaves with somewhat naive expectations about how it should behave. It's for me first clear demonstration that in fact, yes, they are coded in organics. That might sound a bit silly, but like we haven't had that proof. Yeah. Some spectra seem to show hints of organics. There's a lot more compositional information regarding how much water ice there is. Very cool. They have detected both CO2 and oddly CO. So CO2 is neat. We thought it would be there because we find it in basically every other icy body in the outer solar system, comets, for example. CO is a very interesting one, though, because it's not stable. It's sufficiently volatile that it will bleed off of the surface in much timescales much shorter than the age of the solar system.
There's active processing
now means that there's an ongoing process to replenish this CO2. This is actually the part of what Mike and I are talking about in that paper, is discussing how that CO could be there. And quite frankly, that is not something that I ever really wrapped my head around before regarding the compositions, is the influence of CO, because I didn't expect it to be there. And so that's pretty darn cool as well.
There's active processes. Yes.
Yeah. Man, these objects are alive. They're not red and dead things.
Well, I have hope for Pluto then. Pluto will grow one day.
Yeah, exactly.
I might have to wait a while, but
and then finally, on the more distant horizon, there are a number of efforts in the UV. And so from the Canadian perspective, there's this mission concept called CASTOR. I don't remember exactly what it stands for. C is Canadian, A is astronomy, obviously. But the idea is a space-based mirror that will survey the entire sky in the UV, producing photometry, and so images and spectra, at resolutions that match about that from Hubble Space Telescope.
Okay, cool.
So from that perspective, it's like, holy crap, that's pretty amazing.
It's gonna be great.
But for me, I'm really sorry.
Is that an approved mission? Is that
we just last week actually we finished the science review, and that was all stamped. The mission concept is complete, and now I believe we're basically going to have to ask Parliament for funds, something like that. Don't quote me on that. That's not. I'm not exactly where it's at, but if it were to fly, it would be 2028, 2030, something like that.
Cool.
And it's going to provide that U-band, detailed U-band compositional information that I've talked about a little bit here, which is really, really cool, because it'll tell us a lot about the organic structures that we're seeing on the surfaces.
Nice. Nice. Well, I really look forward to seeing this topic develop over, let's say, the next 5 to 10 years. It'll be very cool.
You both, man.
No, I won't. Very cool. And that will do. Wes, thank you so much again for walking us through this very awesome PSJ article. And that will do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye-bye.